Expeditions to Mars are very much in the news lately for various reasons. Recently, we saw news reports about Ingenuity, which is NASA's drone helicopter that flies around on Mars and sending visual images back to Earth. Now, the questions that arise in my mind is, how do you control this from Earth, and what technology is behind it? What is the goal of this specific Mars mission? How did they get the equipment onto Mars? What was learned so far, and how does it impact our lives on Earth? Is South Africa involved in any way? Now, I'm very glad to introduce Professor Rene Laufer, who will give us some insight into this and more. Professor Laufer is currently the head of subject, chaired professor of Onboard Space Systems at the Lulea University of Technology's Department of Computer Science, Electrical and Space Engineering in Lulea, Norrbotten, Sweden. I hope I pronounce all of this correct. Lulea is a coastal city in Swedish Lapland. Norrbotten County is the northernmost county or ion of Sweden. It is also the largest county by land area, almost a quarter of Sweden's total area. When I spoke to Professor Laufer for the first time 2 weeks ago via Zoom, he was lightly dressed and said it is 3 degrees Celsius in Lulea. They are really getting warm summer days now, he said. Now, it gets up to, or maybe I must rather say it gets down to minus 30 degrees there in winter. So no wonder he's researching life on Mars. It's not that different temperature-wise. Professor Laufer is very familiar with South Africa and specifically with the University of Cape Town. He's been here many times in the past. So, Professor, thank you very much for your time and willingness to address us all the way from Sweden this morning. And now it's over to you.
Thank you very much. Thank you very much for the invitation.
Sorry for that.
It is really a pleasure to speak to you. My connection also to your circle of experts and interested, as Johan said, nerds, and I'll join you with that description because I count myself into this group, is a long-term friend and colleague, Sias Mostad, who of course is a very iconic figure in the space sector in South Africa. I had the pleasure to teach for many, many years, about since 2014 at the University of Cape Town, and being there every year, except last year, to teach several courses there, often spending a month or more in South Africa. One of the few happy places I enjoy being there. So I'm always happy and I'm always glad when I have the opportunity to come to South Africa. So let's talk a little bit about Mars expedition. And as Johan already mentioned, I'm quite familiar with some of these topics because I had the pleasure to start my career actually as a young engineer in the field of space and in particular Mars exploration. I'm from Germany, from Berlin. I studied at the Technical University of Berlin, and right after studying, I started my career as a young space engineer at the German Space Agency in the 90s, in the early 90s. And during that time, I was very lucky to be involved in many planetary missions, as you can see here. Some of them didn't make it to Mars. That's a common risk that we share in spaceflight. Some of them made it to Mars. Some made it even further into the outer solar system, as you can see here. And I worked approximately 10 years in participating in planetary exploration missions through German Space Agency and their partners. Typically, all these missions, as you have seen, are very, very international. Often you see many nations coming together and providing payloads, subsystems, spacecrafts, rockets, launch vehicles. ground segment elements to make these missions happen. Afterwards, I was for several years at the University of Stuttgart, starting then to teach my experience from planetary exploration and provide that to students. And then about 12 years ago, I moved to Texas, one of the partners of the University of Stuttgart, to help there establish space engineering track and a space engineering laboratory and research group as part of the university there at Baylor University. And at the same time, approximately at the same time, I started also teaching at the University of Cape Town, thanks to another dear friend and colleague, and was also involved in research and working with graduate students and PhD students. As you see from the many little red needles, these are all the places where I had the pleasure also to lecture and teach in person, all before we switched mainly to online activities. And now, since fall last year, I'm here in Kiruna, which is about 350 kilometers northwest of Lulea. So it's not on the coast, it's quite inland. And some of you may know that this is very well known because Kiruna is also the site of S-Range, the European launch site for sounding rockets and high altitude balloons here in Sweden and used by many European partners. And soon, starting next year, we hopefully will see the first orbital launches as part of the new space activities. You know, companies, commercial companies who build small launch systems, so-called micro launchers, and want to launch from here. So it's actually very interesting times, very vibrant community. Of course, for me, a significant change from Central Texas with 45 degrees Celsius plus in the summer for about 3 months in a row to minus 30 degrees Celsius in winter here in Kiruna and snow for about 8 months a year. So let's come to planetary missions and in particular Mars. And I'd like to remind you, and I'm sure many of you remember over the course of their life, reading headlines and in the newspaper, seeing news items in TV, documentaries about it, that we sent out a lot of exploration missions into the solar system. And this is a list that is quite up to date. And it's a list that just lists the program names. So behind some of these programs like Mariner or Luna or Lunar Orbiter, Apollo, or a Mars exploration program, there are several missions, sometimes more than 20, like in the case of the former Soviet Union's Luna program with 25 successful missions. Some of them only represent here one mission, like Grail or Galileo or Cassini. So just with this list, you can see that we sent out a very, very large number of missions. And Mars is certainly one of the objects in the solar system where we sent a lot of spacecrafts for exploration. Not as many as with the Moon. Our closest neighbor in our vicinity was visited by already about 90 spacecrafts over the history of spaceflight, but Mars is almost close behind. That said, I think it's important to remind you that we live like in a golden age of planetary exploration. I'm sure many of you remember that, let's say back in the 1980s, it sometimes took a year or two until you read something again in the newspapers about another planetary mission arriving at its target. So it could sometimes take a year or two before you read again something that a spacecraft, a space probe was sent to another planet, orbiting the planet or landing at the planet or even just flying by that planet. In today's world, we see specifically that we have so many missions going on in parallel today that it would be more than a full-time job if you would decide that you would like to follow on the internet each of these missions and read every press release, read every mission report, read about every picture that is released, and even harder if you would like to follow every publication linked to these missions. The reason for that, of course, is that spaceflight and the history of spaceflight is continuing, and several of these missions are actually active for quite some time. Let's give one extreme example here in the upper corner, the Voyager probes. Both were launched in 1977, and they are still operational with a technology on board that is from the early 1970s. They were sent out on the so-called Grand Tour, flying by Jupiter, then Saturn, and Voyager 2 even flying further and do flybys on Uranus and Neptune. And now, since the late 80s, since 1989, these probes are basically flying outwards, leaving the solar system, having enough velocity to really escape the gravitational grip of the sun and flying outwards. And for a few years now, we can say that they are kind of at the edge of the solar system at approximately 100 times the distance that Earth has from the sun. When you also see this list here, then you see a lot of Mars spacecraft orbiting Mars or having landed on Mars or roving on Mars. And here we see a similar effect. Many of these spacecrafts actually show an incredible endurance and an incredible long-lasting mission duration due to their good design and due to the fact that everything was planned with very, very significant margins, something that is always important in spacecraft design. We come back to this picture when we have a look again how many actually are currently operational on Mars. So let's have a quick reminder about the differences and the similarities between Earth and Mars. And no surprise, I'm sure you know that Mars is smaller than Earth. It's not the closest planet to us. That's actually Venus, that comes a little bit closer to Earth than Mars does. Nevertheless, with Mars visited so often, it feels like, you know, the neighbor we know best. Yeah, even if it's a few meters further down the road than the other neighbor that lives next door, but is maybe a little bit more quiet. So Mars, smaller than Earth, as you see from the diameter, almost half the size of Earth. Due to that, approximately 40% of the mass of Earth, and therefore also here precisely 38% of Earth gravity. So probably sometimes the effect we would wish, you know, after a long winter, when it comes to the moment when we want to be ready for the beach again, on Mars you get on the balance and you basically just, it's 38% of what you weigh here on Earth. Mars is further outwards. As you can see, it's almost 50%, approximately 50% further outwards than the Earth, with over 220 million kilometers. And you can also see that what is received at Mars is less than half of the sunlight in intensity and energy that we receive on Earth. So that has significant effects, of course, on the atmosphere, on the climate on Mars, on the temperature effects, on weather and similar things. Mars is orbiting the sun further outwards, so the period that Mars needs to do this is certainly longer. You see here it's 686 Earth days, so almost 2 Earth years. Mars has seasons like the Earth, and here we see the similarities. You see on this picture that Mars' axis is almost exactly as much tilted as the Earth axis, and the rotational period around its own axis of Mars is only slightly longer than Earth's period of 1 day. So basically, you spend about 35-40 minutes more on Mars for a day than on Earth. If we would not have a watch, psychological studies showed that our inner clock usually adjusts itself somewhere in the range of 20 to 28 hours. So we would not even notice that the Mars day is slightly longer. Nevertheless, it has significant operational consequences. Because if you operate a spacecraft on Mars, in particular a rover on the surface, then it means you basically have to live in your operations center on Mars time. But it also means that your Mars day shifts compared to your Earth day every day by 40 minutes. So that also means your working time basically moves along. It's kind of a constantly changing shift work. So you might start when your mission lands basically with the same work time on Earth and on Mars, but over the next few days and weeks, basically you shift from a day shift to a night shift, and then very shortly, a few days, weeks later, back again to a day shift. So this is a constant process that everybody goes through when you do missions on Mars, in particular on the surface. The atmosphere on Mars is certainly different. You can see here the major difference, and that has also consequences for drones, an example, what we see right now with this little helicopter as a technology demonstrator on Mars, because you can see the atmospheric pressure is basically only 1% of what we see on Earth. So very, very thin. So you need to make significant efforts to create the same lift to bring mass up in the air. And of course, also the composition is different, with carbon dioxide basically the main component on the Martian surface. The temperatures, therefore, also different. And as Johan already said, it comes quite a little bit closer to what I encounter here. A good hot summer day on Mars can be about 15 to 70 to 20 degrees Celsius, but it gets really, really cold on winter, much colder than here on the coldest places on Earth. So many probes have been to Mars, and there are many probes at Mars, and actually it's not just the traditional players that we remember from the starting time of the era of spaceflight, with the United States on one side and the former Soviet Union on the other side. Today, Mars exploration is a very, very international business. And you can see this from the pictures here. European space agencies involved with spacecrafts around Mars, like Mars Express or the ExoMars Trace Gas Orbiter, and hopefully soon also with a rover and a lander on the Martian surface at the next opportunity. Of course, NASA, the US Space Agency, launches almost every opportunity, almost every 2 years, orbiters and or rovers to Mars, and has many spacecrafts around Mars with very different purposes, from high-resolution imaging of the surface to atmosphere and climate observations. India launched their first Mars probe, Mangalyaan, a few years ago. China launched a spacecraft to Mars with an orbiter and a lander and a rover that just landed recently. So it is a very international business. Even in recent times, we have seen, an example, Japan sending spacecraft to Mars there with some difficulties, because Mars is still quite hard when it comes to get there and actually to operate your spacecraft. So we have landed actually also on quite a significant amount at places on the Martian surface. And again, this is quite an international business. Most of the dots you see here, the green ones, are NASA landing sites, US landing sites from the mid-70s, with the famous Viking probes, the first probes that were trying to identify life on Mars with their instrumentation. We know from today's perspective and the progress we made in between that these instrumentation, state-of-the-art back then, would not have been able actually to identify signs of life on Mars or traces of life on Mars. So this is part of the normal scientific process to improve. And so new methods were found, and we look with different and more refined methods for traces of life on Mars. What you see here is also a kind of a topographic map in a false color scheme, and it shows actually that Mars back billions of years ago was divided in large ocean and highlands, where you'll see all the craters, and of course the lowlands, the blue scaled, the blue colored areas for the oceans, where probably water was available in significant amounts. Also, it is most likely that the atmosphere had a much higher density. Mars with a lower gravitational force, but also without a magnetic field, was certainly not able to contain the atmosphere and keep the atmosphere, and so the molecules of the atmosphere were lost into space over billions of years. You see also some of the other landing sites, the Mars probes of the former Soviet Union, also attempts to land on Mars that were not that successful in the 1970s. Also landing sites like Schiaparelli and Beagle, the unsuccessful attempts of European Space Agency to land on Mars, and very, very recently, just a few days ago, the Chinese landing site with their lander and the rover Tianwen-1. So let's come back to the golden age image. And what I show you here is actually everything that's framed in red are the ongoing missions at Mars. So actually there is quite a lot of space probes on Mars. And some of them, like 2001 Mars Odyssey, are there for 20 years now. And that's an incredible amount of time for a deep space probe, especially when you think of the harsh environmental conditions in space, especially in deep space, beyond really the protective magnetic field around Earth that helps us, especially in particular with our low Earth orbit satellites here that are not exposed to so much harsh environments in terms of radiation and particles. So you see also several landers are still operating on Mars. Several new probes just recently arrived. And the 2021 class, let's call it that, the 2021 class of Mars spacecraft is as diverse as it could be, actually, and represents really the very, very international efforts we see now here in Mars exploration. First, it was HOPE, the first Mars mission and first planetary mission, actually, of the United Arab Emirates, who has actually a very, very ambitious and enthusiastic and very well supported space program with incredible facilities in the Emirates and university programs, educating a lot of engineers. So really a domestic program with a lot of local human resources and capacity building and human capital on their own to make their space program happen. And HOPE was their first attempt to go to Mars. While this was a space mission by the United Arab Emirates and is operated from there, it was not built there. Mars spacecraft and planetary spacecraft needs a certain experience, and to increase the chance of success, the spacecraft actually was mostly built in the US with collaboration of famous universities like University of Colorado's campus in Boulder, with a famous LASP laboratory who has significant experience of 4 to 5 decades building spacecraft and instruments for Mars. The most recent one, the New Horizon probe that was flying by Pluto a few years ago. And also the spacecraft bus was supported by US space industry companies, but payloads came, of course, from the United Arab Emirates, and there were international collaborations, as it often is the case with all these space probes. When we think about American space probes, European space probes, Chinese space probes, we should not forget that in today's world, typically, we see a significant amount, often half of the number of payloads coming from other countries. The participation in science became very, very international, and it's very common to see collaborations from 2, 3, or more continents. HOPE arrived beginning of February in Mars orbit, was launched by a Japanese rocket, actually, and arrived there after the usual 6 to 7 month journey to Mars. And what you see on the bottom is actually the first image that HOPE transmitted to Earth from Mars. HOPE is focusing in particular on the climate and the Martian atmosphere and the surroundings of Mars. It is kind of in a higher orbit. It's not as close to the surface than other orbiters, and tries to get a good overview to have an understanding what actually happened to the Martian atmosphere in the past and what happens now to the Martian atmosphere, so we can study and try to understand these mechanisms in comparison also to the mechanisms we see on Earth. Shortly after, Perseverance, the Mars 2020 rover mission, arrived on Mars. One of the big NASA missions again, the second large rover actually, basically the twin of the Curiosity rover that landed on Mars a few years ago. The reuse of a significant amount of hardware and rebuilding and re-engineering basically the established, well-tested chassis and most of the structure and subsystems for driving with the rover were used here, including the lessons learned, what to do better compared to Curiosity. And so Perseverance basically looks like a twin to Curiosity. You really have to look carefully to see the differences in certain payload elements or some of the payloads that are at the end of the famous long robotic arms. This time we had more cameras on board, and NASA provided spectacular views here with the landing of the rover with the famous sky crane. We will see this in a later slide a little bit more in detail. And you'll see here cameras pointing down to the rover just shortly before it touches the ground, and actually up to the parachute that was helping the accelerating the whole landing craft, basically the sky crane and the rover. And if you were wondering about the strange pattern of that parachute, there is actually a reason. The scientists and the engineers who developed the parachute and painted it coded kind of a hidden message in it, and it is the unofficial motto of the Jet Propulsion Laboratory of NASA in Pasadena, California: "Dare mighty things." So that is kind of a little hidden joke here that the engineers did with color coding the inner part of the parachute. Nobody knew about that until the parachute was unfolded. Only a handful of engineers knew about it. But as it is with the internet, worldwide, globally, many people immediately jumped on that, and within a few hours, people posted on the internet the decoded message having found out the binary code that was used here to put this message on the parachute. I think this is a wonderful outreach idea to make things like this more popular. Perseverance is not alone. For the first time, the Mars rovers brought basically a little companion, Ingenuity, the little helicopter. Well, it is still about 2 kilograms in mass. And as I already said, flying on Mars is difficult because due to the very thin atmosphere, basically 1% of the density we have on Earth, it takes a lot of effort to create the lift that is needed to bring mass up from the ground, even if you miniaturize it, as it was done here with Ingenuity. The idea to use a helicopter was already popularized over many, many years by engineers and scientists, and many publications studied that, because if you would try to do it with a plane, even a gliding plane, you would incredibly large wingspans. And that certainly would have been difficult to first bring on Mars, assemble it, or even as a folding structure, and put then that plane into the atmosphere. Don't want to say into the air, to fly. So with a helicopter actually here as a dual propeller helicopter, there are much more possibilities to do this, because you can much more control the rotational speed. And with very strong electric motors, you can increase the rotational speed so much that it will help to bring up the helicopter from the ground. And you see here on one of the images where the helicopter itself took a picture, kind of an indirect selfie, of its own shadow over the ground. Ingenuity is a technology demonstrator. Many people ask, so what is Ingenuity doing? How is it helping Perseverance to do its mission? Well, for this mission, that's not the idea. Ingenuity is there to basically demonstrate that such little vehicles, drones or something like this could be useful for the rovers, because don't forget, the rovers only have the possibility to see what they can see from with their own cameras. So there is no view a little bit from the higher ground. There is no look beyond or a glimpse beyond the horizon before you drive there. So you have to drive there to discover that maybe that drive was not worth it from a scientific point of view, and you should have driven in a different direction. So for future missions, the idea is to have little vehicles like Ingenuity, hopefully with a longer lifespan, but probably several of them to increase, due to reliability issues, to increase the number of drones you have, and use them kind of as little scouts or outlooks high above your rover. Currently, Ingenuity is very, very limited. The connection to the rover is basically about 1,000 meters approximately when it comes to sending data. And it's interesting that a lot of the components you see here are actually commercial off-the-shelf components. The batteries are Sony batteries, lithium-ion batteries that are also common in mobile phones. The IMU, the inertial measurement unit, you know, with a gyros on board to fly that, is actually a smartphone-ready IMU from the German company Bosch that you find also in commercial smartphones when you want to use it for gaming and things like this. So you see actually a lot of commercial off-the-shelf components here that were made space ready, were tested for space, and they work, as we could see now, very, very well. I hope we will see a few more flights. A few more flights are planned for the coming weeks until Perseverance probably leaves the distance it has to Ingenuity. And of course, very, very recent, we have seen the Tianwen mission landing. The orbiter arrived already a few months ago in Mars orbit, used the opportunity to make detailed high-resolution images of the potential landing site. And then with that, the entry, descent, and landing happened, and the rover was already deployed. Perseverance, of course, as it is a long-term goal of NASA, continues the work of Curiosity that is still active and operational, and hopefully will be for many, many years, to search for signs of life or traces of life. And Perseverance has additional complementary and refined instruments on board to do this. But it is also the first step, hopefully, to bring back in about 10 years, maybe, samples from Mars. The first time that we get, hopefully, then samples from the Martian surface back to Earth to use really the opportunities we have on Earth laboratories. Should not forget, when we usually say a picture says more than 1,000 words, then my geology friends always say a rock says more than thousands of pictures. And as great and as high-tech these vehicles on the Martian surface are, their payloads are still limited in the range of a few kilograms or maybe above 10 kilograms. That's not compared to the capabilities we have on Earth with really, really sophisticated laboratories to study the rocks here. Tianwen-1 tries to do similar things. The main scientific purpose is much more traditionally more in the geological understanding of the Martian surface. It's China's first probe sent to Mars. But it also, like Perseverance, the rover shall collect samples. And as with Perseverance, this is the first step also to a possible Chinese sample return mission, also planned for the 2030s. So we will see who's collecting their rocks first and who is maybe having the more interesting rocks. Landing on Mars is not easy. It always looks like this, but it is not. NASA coined the term or the motto 7 minutes of terror actually several years ago, because it takes approximately 7 minutes from basically approaching Mars and starting to enter into the atmosphere of Mars until you touch down on the ground. And if that sounds short to you, it's actually basically the same amount of time you need to take off. When we launch an example here from Earth, it takes us about 8 minutes until we are in low Earth orbit, and the same would be the same for Mars. So what we usually see on Mars as a body with atmosphere is a similar procedure we see with landings on Earth, be it with astronauts, an example, you know, capsules entering the Earth atmosphere, then a parachute is deployed, and then either, you know, short retro-firing rockets fire moments before the landing with a Soyuz, or you land in water like with a Crew Dragon. On Mars, there are different approaches depending on how you want to land and what you want to land. An example with landers, it is very common actually to see that you enter the Martian atmosphere, and don't forget, you basically enter with about 20,000 kilometers an hour into the Martian atmosphere. So the atmosphere becomes a plasma, is heating up incredibly around the capsule that enters the atmosphere, the Martian atmosphere. The heat shield, a heat shield is necessary to protect the lander or the spacecraft or the rover. And only when you're through basically the atmosphere, lowering down and dissipating a lot of energy, then you pull a parachute, and that is at a much lower velocity. That parachute basically pulls you in a moment's notice from supersonic velocity, from more than the speed of sound, which is slightly different than the Martian atmosphere, to immediately in a moment's notice, so this is quite of a harsh break, under the speed of sound, and then you basically land with a parachute until you get close to the surface. And then usually on Mars, we use then powered descent. The reason for that is that with a very thin atmosphere, you remember 1% of the density of the Earth atmosphere, a parachute of a reasonable size that fits into these capsules is not really slowing you down enough. So you need a powered descent, especially with larger mass. You might remember in the 90s or in the early 2000s, we still saw smaller probes landing, and shortly before hitting the ground with a parachute, they basically blew up and inflated airbags around the spacecraft. And with that, you basically then bounced with all these airbags around your spacecraft many, many times on the Martian surface. So this is not used anymore because it doesn't work really with large masses. When we have these stages, it is very correct to say that basically in each stage, a reduction in energy by 90% is done. So first of all, 90% of the energy that you have when you come in is basically you're breaking down, and you reduce your energy by basically 90% through the re-entry and the heating up and the slowing down in the atmosphere with these high temperatures. Then from the remaining 10%, the parachute takes another 90% basically, and only then from the remaining 1%, basically the powered descent takes the remaining effort to land you softly on Mars, because you want to go down from 20,000 kilometers an hour to 0 kilometers an hour. And we learned a lot over the years, over the Martian atmosphere, and you can see this actually in the picture on the bottom. These are the landing ellipses. These are the uncertainties that we had with earlier missions 20, 25 years ago, where you see that some of these landing ellipses were about 200 kilometers long and 70 kilometers wide. These were the uncertainties where you land. Today, with every landing, we take a lot of data. We make a lot of measurements from Earth, even with the ground stations, and refine our model of the Martian atmosphere, and refine now that you can see here, it basically goes down to about 10 by 10 kilometers. So what are the important elements when you're on Mars? Power is one of them. You need power to operate your spacecraft. Common method, of course, as we all know with spacecraft, is solar arrays, but some of the rovers are so large now, they use actually radiothermal generators. So these are systems that are running on the radioactive decay of plutonium, and the heat that is dissipated through that is turned through a thermal element into electric energy, which creates a larger amount of energy for a longer time, because solar arrays are prone to degradation, and with Mars having an atmosphere and sandstorms, you have also the effects that more and more your solar arrays are covered by dust. Nevertheless, even with solar arrays, we have seen that many spacecraft last a long time. So the famous Opportunity rover that just ceased its operations a few years ago was basically for 15 years in operation compared to the originally planned 180 days. So that works, but it shows also limitations. The rover basically did approximately a little bit more than a marathon. So a little bit around 45 kilometers in 15 years. Every astronaut that would be on Mars with a rover and drive by herself or himself would basically cover that distance in a few hours and still do the same scientific work. Communication, of course, is also important. Mars is far away and the distance is changing constantly. So you have a delay one way of 4 to 22 minutes, depending if Earth and Mars are on the same side of the sun or on opposite sides. That means you really have to wait a significant amount of time for your answer. So there is no real-time operations. How does it work, actually? Well, traditionally, in the early days, every spacecraft brought its own communication system. That takes a lot of space. And we still do this. You can still see that the rovers or the orbiters around Mars communicate with Earth in the X-band range. So we're talking here with frequencies around 10 gigahertz. And they basically use then the deep space network on Earth to collect these informations. But also the rovers on the Martian surface have X-band systems to directly connect to Earth. And I move a little bit. The data rate is quite slow. So you see here, you have approximately, at the best case, 32 kilobit per second. So to improve this, we use for many years now the orbiters around Mars, and that's why we like to have them as long-lasting as possible, as relay stations. And that's actually a very interesting international approach. So Japan's JAXA, Europeans ESA, and the US NASA space agency agreed for a long time on a standard, and they put into all of their orbiters and in their rovers the same Electra system, which is kind of an internationally agreed, interagency agreed standard for communication. It uses UHF bands, so basically amateur radio frequencies. And with these payloads, you basically can connect to every other orbiter. So that means Europe's Mars Express actually supports NASA's rovers, and then vice versa. So that works very well. It's actually also quite interesting modern technology. What you see here, the Electra payload, is actually a small compact box that you put into your orbiter and into your rover. And it's based on a software-defined radio, you know, these little USB sticks that you can buy on the internet and allow you to basically listen to a wide range of frequencies. It's FPGA based, so field programmable gate array, very modern architecture of systems that can be reconfigured with new software. And it's running RTEMS, which is an open source real-time operating system. So it's actually things that we hear also in the software area when it comes to computer projects. Sometimes it takes even more than just the relay orbiters on Mars. And we have seen this actually, that it sometimes makes sense to even bring your own relays. The Mars InSight mission, when it landed, had the disadvantage that the landing site was not in line of sight to Earth. So there was no direct communication possible during the very critical landing phase. And no orbiter was, from orbital mechanics point of view, was in a position to observe that. So NASA tried for the first time actually going with another very new product, actually with CubeSats, and building two identical 6U nanosatellites of about 13.5 kilogram mass. So you see here an example with a 30 by 20 by 10 centimeter size satellites called Wall-E and Eve, after the Disney movie Wall-E. And they were basically built to fly with InSight the lander to Mars on the same rocket, and then provide the line of sight relay function just for the half an hour critical time frame shortly before and after the landing. So that shows if it's necessary, you can do that. And again, they did this using these amateur band frequencies in the UHF band with about 8 kilobit per second and retransmit this via X-band then back to Earth. So how is it to operating a spacecraft on Mars? Well, normally people sit, as you I'm sure have seen, in these big mission control centers like at NASA JPL, or now with the Chinese mission at the Beijing Aerospace Control Center here in these large rooms, mission control rooms. And of course, you need large antennas on the ground, like in example, the Deep Space Network antenna. I tried to get out of the way. The Deep Space Network antenna here in Goldstone, California, the 70-meter dish. But of course, the pandemic forced everybody to change. So you see here with pictures that NASA employees who control the Curiosity rover basically set up everything for their home office to now via secure connections and via firewalls and set up systems to control basically the rover from home. How are they doing this? Again, they use a lot of open source architecture. OpenMCT, Open Mission Control Technology, is a software package that is not only used by NASA, but also used by universities for their CubeSat missions. And you see here one screenshot, and as usually, it's not that spectacular, because it's not like in a science fiction movies as if you're sitting in the cockpit. You have a lot of graphs and a lot of status displays to show you how the rover is. Well, sometimes spacecraft even have the opportunity to do a little bit of a touristy thing and take pictures of each other. And we became more and more better with this. You see here in the initial years, you see that orbiters took pictures of other orbiters when they sometimes come as close as a few 100 kilometers, because they're all on different orbits, so that doesn't happen very often. But what is more and more common is to take pictures of the spacecraft that are on the surface. Initially, just a few little bright spots in terms of when you see basically the reflecting solar arrays on the surface. More and more, it was even possible, I think, here in this direction. Okay, I'm not totally in there. In the center, you see basically opportunity, and if you would zoom in, you could even see the boom of the camera and the solar arrays. And what is, I think, the most spectacular is that from the Curiosity and the Perseverance rover, both rovers, orbiters with high-resolution imaging were in the right position to take pictures during this 2-3 minutes of parachute phase. So you see here really basically the real image where the parachute was deployed before the rovers were landing, and that observed from an orbiter around Mars. I think that's spectacular. Of course, taking pictures on Mars is not as simple as you think. And Du hast den Farbfilm vergessen is a very famous song from the 1970s in Germany. It basically says you forgot the color film. So now our holiday pictures all look black and white. So to make sure that your pictures actually look correct, it is not as simple as like taking a picture with a mobile phone. We should not forget that. So when you fly cameras in space, they degrade, optics degrade, chips degrade, the radiation, influences the electronics and the quality of the chip. So it is actually important to recalibrate regularly your camera and basically check if red is still red, green is still green, blue is still blue, and white is still white. Professional photographers know what I'm talking about. And what you see here in the big picture is one of these so-called calibration targets. Good opportunity to also put all the flags of the countries that participate and the logos of the space agencies that participate. And on the bottom, you see something that some professional photographers know too, a grayscale image for calibration. So all of this is necessary to constantly keep the quality of the imagery correct, because we get digital imagery, and that means we need to recalibrate the image values we transfer from Earth. The same goes with geometric imagery, so to make sure that the images are still geometrically correctly with the right angles. So a little family portrait here with the depictions of the rovers will help with that. If you're interested in getting the data from these missions, you might be surprised that they're actually very, very widely available. After a short period where basically the scientists have the opportunity that the data are only available for them to make sure that the science they plan to do, they have the opportunity to publish first their results. So often after basically about 6 months, the data from these planetary missions, at least from the large agencies like ESA, NASA, or Japan's JAXA, are freely available, typically in the raw format. So you have to really make an effort to think about what you want to do with it. But an example with NASA's Planetary Data System or ESA's Planetary Science Archive, you can basically download raw imagery of these images and start your own image processing with data from planetary science probes. And it's really a huge amount of data, not only imagery, but also non-imaging data, magnetometers, weather data, and other stuff. So how is South Africa involved? Well, I'm sure many of you know that since the 60s, Helderberg was used as a deep space network station by NASA until the mid-70s. And in example, some of the first images from NASA's Mariner 4 space probe to Mars in 1965 were actually received there. Nowadays, it's used as a radio astronomy dish, HARD-RAO, Hard Radio Astronomy Observatory. But from time to time, NASA still asks for support, especially for missions into deep space after launch, depending on the trajectory. When you have the better connecting line of sight to the spacecraft from South Africa. The last time they did this was actually in 2011 with the Mars Science Laboratory, with the Mars exploration, with the Mars rover Curiosity. Just last year, South African National Space Agency and NASA signed a new agreement that in future, South Africa will again provide on the new site, Matthiasfontein in the Western Cape, building up a new deep space network station with modern technology provided and work in collaboration with NASA to support future missions, including human missions to the moon and hopefully in future also to Mars. So South Africa is back actually, at least in the ground support business. And I hope to see in the future also maybe payloads from South African universities and research organizations participating in these missions. So at the end of the day, and after my talk, let's not forget that actually getting to Mars is really difficult. So not only is it important to do it at the right time, so only every 26 months we have from orbital mechanics point of view, the right position that we can launch something from Earth and at the minimum energy needed that we can actually just make available with our chemical rockets, launch something that flies to Mars on a 6 to 7 month journey and basically hits Mars then when Mars is actually at the right point in the solar system. When you think of normal rockets, then we should not forget it's really, really hard. The same rockets that you see here that normally are able to bring about 10 tons or 20 tons even into low Earth orbit, like to the International Space Station, like the Soyuz or the Atlas rocket here. And don't forget, for planetary missions to Mars, we talk about 1 order of magnitude less payload capacity. So what is 20 tons into low Earth orbit, an example to supply the International Space Station, is basically 2 tons into Mars orbit and only 1 ton to the surface. So you need still the same large rocket to just bring a 1-ton rover to the Martian surface that you would normally use to bring a lot of cargo and many astronauts to the International Space Station. It is that difficult, and that can give you a little imagination and a glimpse how difficult it will be actually and how large the spacecraft has to be to actually fly with a crew with human astronauts to Mars, hopefully in the next 10 to 15 years in that time frame. So that said, let me always end with something that I think is also something you can take with you to the next party and impress people. Because I always like to ask people when it comes to launching, what is an important element of a launch? An important element of a launch is, we all know, the countdown. So why do we actually have countdowns? Who came up with the idea actually that we should count down in time before we launch a rocket? Because that has not been done with ships over the history, that has not been done with planes or something like this. And I always like to tell people, this is the next time you can impress friends on a party. The reason why we have a countdown is a German silent movie from 1929. Fritz Lang, famous silent movie director in film history, German movie director, the James Cameron of his time, making movies like Metropolis, Dr. Mabuse, and Woman in the Moon, Frau im Mond, where he made the first realistic science fiction movie in movie history. And he actually asked his wife, who was his script author, Thea von Harburg, how to film basically the scene to depict the launch. And he asked also, one of the first directors who did, experts. So he brought in the new type of science consultants for a science fiction movie. Oops, it doesn't work. I thought I can show the movie. What he did was he filmed basically the script, and these science experts basically told him, early rocketry pioneers, you know, in the 1920s, before spaceflight really took off, he asked them, so how is it when the rocket launches? When does it happen? And they told him, well, if everything is ready, somebody presses the button and then the rocket launches. So he filmed it that way. The test audience was not really impressed. There was no drama in it. So he went back to his wife and asked, so how can we make this more dramatic? So she said, well, let's count. So they counted, you know, silent movie, you have these plates in between with the text. So 1, 2, 3, 5, 4, 6, 7, and so forth. The test audience still was a little bit not impressed, because they said, how do I know when the launch happens? Does it launch at 5, at 7, at 49, and 92? Who knows? So he went back to his wife and they came up with the idea, let's count down. There's the drama. And that's how the countdown was developed, because several of the young, enthusiastic rocket pioneers of the 1920s and 30s saw this movie and took this with them when, of course, during the Second World War, for military reasons, they built the first rockets. And after the war, when these German scientists and engineers built rockets then in the Soviet Union and in the US, and they took the idea from that movie with them to have a countdown when launching rockets. That said, as always, also like to tell my students, and I think you're as enthusiastic as they are, virtual science and exploration are not an option. So we really have to go exploring. You can't really do Mars exploration just on your mobile phone. You really have to get there. And that said, I'm available for questions, and I see already the first question here from Bernard. How do the missions in the search for life prevent life, such as bacteria, being transferred to Mars? That is a very good question, and it's a very hard question. So there is the so-called Planetary Protection Protocol. It's an internationally agreed protocol between space agencies on the committee level on the United Nations. And we have different levels. Mars has one of the highest level. So the moon has a lower level, in example. You know, we know on the moon there is no life, so there is nothing we can contaminate. So you still have to clean your spacecraft before you launch it to the moon to not bring something there, because we know that certain bacteria and viruses actually can survive in space for a long time. That's also interesting for the astrobiologists, the exobiologists. When it comes to Mars, you really have to make incredible efforts to keep your spacecraft clean. That means not only chemically cleaning it, but also radiation is used to basically kill all bacteria and viruses you have on the surface or inside of your spacecraft. Nevertheless, we know that today we can do things we were not able to do 35 years ago. So from today's perspective, when you talk to the planetary protection officers, and space agencies like ESA or NASA have planetary protection officers, they have to sign off the document before the spacecraft is launched into space. And that said, we know today that in earlier times of the space era, we are sure that we were not able to clean the spacecraft as much as we do today. So we cannot rule that out completely, that we already brought some contamination to Mars, even if it's only maybe on a very local level. And that said, it's something where scientists all over the world always say we have to make an effort to do this as good as possible. But it also means if we want to search for life, then we have to be sure in our methodology and our instruments that we use that we are not basically taking something we brought from Earth with us as life that we found on Mars. So we have to make sure that we have methods to differentiate that, because we cannot be 100% sure that we are able to do full planetary protection and clean the spacecraft completely. It's a complicated topic, and it will be more complicated the moment we land with humans on Mars, because at the end of the day, then it is much, much more difficult to keep everything in the planetary protection protocol. You know, with a spacecraft, you can basically use cleaning methods, chemically, radiative, and others, to clean your spacecraft to kill everything. You can't do the same with humans because you don't want to kill the humans. So it's difficult. Humans will bring bacteria, viruses, and things like this to the Martian surface. Other questions?
Rene, you, man, I feel so clever now. But yes, I've got one other question. Maybe you did answer it and I didn't follow it. But this little drone fascinates me there. My question is it pre-programmed completely and it operates now for long periods of time based on software built into it, or can they control it from Earth and make changes to the software?
Actually, both. And we see this with all the spacecrafts we fly today. So we know that it is important to have pre-programmed software on board of the spacecraft, because due to the delay in the communication, in example to Mars, minimum 8 minutes, two-way communication, 40 minutes or longer possible. You need pre-programmed software that is able to operate a spacecraft, the little helicopter, Ingenuity example, autonomously. Nevertheless, we learned from early spacecrafts that it is necessary to have the possibility to change the software on board of the spacecraft. Lessons learned due to that, because we should not forget, we go to places where we have never been before. It's basically, you know, like a rally without having a map. You don't know what's around the next corner. That means you might have to adapt in your conditions, and you might have to adapt your software for operating your spacecraft, even improving your spacecraft over time. We have seen this with other spacecrafts. In the case of Ingenuity, it's actually that Ingenuity is controlled from Earth, but not in real time. So every flight is very carefully programmed, first on a simulator on Earth. That's a computer environment that behaves basically with all the physical laws and the hardware of Ingenuity in software on the computer. Then you usually test also the software on what we call the flight model 2. It's basically the same hardware. You build everything twice and you have it on the ground. You will not fly under Mars conditions on Earth, but you can get close. You know, you can put it into a vacuum chamber and reduce the pressure down to Mars pressure. Still, it's Earth gravity. And only then, when all these programs and commands are tested, then they are sent to the rover. The rover sends it to the helicopter, and then they are executed, but autonomously. So there is no real-time control because of these many minutes of delay. And that's why you see these stepping stones being very carefully in the beginning. You have seen, and I'm sure you all remember, Ingenuity basically was commanded to basically turn on the propellers, spin up, lift up a little bit, not moving actually in any course direction, and landing at the same spot. And do this again and again. And only with a recent flight, basically, they did for the first time, going into the air, moving into one direction and landing at another spot. Again, all of this is done autonomously by the helicopter itself, but it is all commanded from Earth. Other questions?
Thank you.
Pleasure.
Anyone else with a question for Rene here? Rene, I think we are all overwhelmed with knowledge now, and
that is fine. That is fine.
I feel like I'll apply now to go to Mars after this.
I think that is great, because, you know, one of the important things is that if you're over 45 and 50, this is basically when you come into the right age afterwards to get to Mars. because you know, you have the experience from your work life. You are done with the family planning. Yeah, you can certainly, your body can certainly more easily deal with the harsher environment. Also, when it comes to the effects of the harsh environment of space, because there is no risk anymore with any damages to parts of your genetic code or something like that. So actually, we always assume that the astronauts that will go for scientific reasons to Mars will certainly be astronauts in the very late part of their career, to have actually all the experience you need. Often what we expect is to have astronauts, often maybe even with more than one career path, even more than one field of work. So it's not enough to be just specialist in one field. For sending a crew to Mars, you have to have experience in different fields to overlap with other colleagues and certainly cover also and support them.
Yeah, and I see Jeff has got the same idea as me. The one-way ticket is also not a problem. At that age, you don't mind that it's a one-way. Rene, thank you very much. You've really, and I hope once you can come back to South Africa, we might be able to actually get you back to the U3A in real life. So I'll keep in touch. But thank you very much for your time.
Thank you very much. And all the best. Take care. Stay healthy. Stay safe. And see you then the next time in South Africa.